share screen. And we will share screen and do it the usual way. All right. And maybe we'll enlarge it to make it look bigger. All right, so I'm going to begin with a very brief overview of what we did last time. We worked through a lot of material. And basically, we worked on how the Dirac wave function transforms under Lorentz transformations. So after reviewing how fields transform under ordinary rotations, and then generalizing this to Lorentz transformations for various kinds of fields, we get a guess that the Dirac wave function should transform as shown by this equation down here. That is to say, the argument goes to x goes to lambda inverse x, but the wave function gets multiplied by a lambda dependent matrix 4x4 spinor matrix that in effect takes care of the spin part of the transformation. The x here, by the way, is an abbreviation for the entire set of 4 space-time coordinates. That's what that x right here means. We require that these D matrices satisfy the representation property of the Lorentz transformations. So that was one thing. That was a place we began in the last lecture, and then we actually worked it out in the following way. We took that transformation property for the Dirac equation and plugged it into the free particle Dirac equation, demanding that the free particle solution should be mapped into other free particle solutions by the Lorentz transformation. And that leads to this boxed equation, which gives us a condition on the D matrices, which interesting equation, which can be interpreted by saying that the gamma mu forms a 4 vector under Lorentz transformations, in the sense that if you conjugate it by in effect, the spin rotation operator, that's what these Ds are. What you get is a linear combination of the components, which is given by the classical Lorentz transformation. So this is very close to the definition of what we called a vector operator in the non-relativistic theory, except there it was just rotations instead of Lorentz transformations. Having gotten that, we then specialized this to the case of infinitesimal Lorentz transformations, and we found that they could be represented as an identity plus a small correction, where the theta here is an antisymmetric matrix of small numbers. You see, these are the coefficients of the correction term, and the sigma mu nu is an antisymmetric quote unquote tensor of 4x4 Dirac matrices. Moreover, we were able to determine what that tensor is. It's I/2 times the commutator of the 2 gamma matrices. So once the sigma is explicitly known, the infinitesimal D matrices are known, and then by compounding them, large numbers of small transformations, we can create finite transformations. We did that for both rotations and boosts. First of all, for rotations, this theta tensor only has spatial parts. It doesn't have any either time row or time column vanishes. These are 3 theta angle parameters here are related to an axis and an angle by the formula here, that theta vector is n hat times theta magnitude. And then putting that together, we obtained a formula for the D matrix, which implements a spatial rotation on a Dirac spinor. Basically, the upper and lower 2-component Pauli spinors just get rotated by the standard 2-component Pauli rotation matrix, which is given here in terms of the exponential of the linear combination of the Pauli matrices. This OD matrix can be written in a similar form, except instead of the small sigma, there's a capital sigma. Capital sigma, in effect, is the generator of rotations in the 4x4 sense. And to show you what that capital sigma is, I'll refer you here to a table I'm accumulating of Dirac matrices. There's a collection of Dirac matrices, quite a few of them. They can be broken into those that are used for non-covariant description of the theory versus those that are useful for a covariant description. In the non-covariant description, we got the alpha and the beta, which appeared in Dirac's original formulation of his equation. And this new one, capital sigma, is just 2 Pauli sigmas on the diagonal. That's what it is. But as I say, this is the generator of rotations. All right, anyway, having done that, we got the D matrix for rotations, for pure rotations. Now for pure boost, the theta parameter matrix has only time components and no spatial parts, as you see. It's given by three rapidity parameters, lambda 1, 2, and 3, which we break up, taking them collectively as a vector, we break up into the axis of the boost and the rapidity of the boost, which is the magnitude of this vector lambda. And then by going through the manipulations we need to, we exponentiate the infinitesimal version of this, and we end up with the following expression for the D matrix for a boost. As you see, it's got half hyperbolic angles of the rapidity, caution, sinh lambda over 2, and it's got the axis of the rapidity, the axis of the boost. The axis of the boost is just the direction in which you carry out the boost. So it's the direction of the velocity of the boost. This means the same thing, dotted into sigma, coming here on both sides. So anyway, this takes care of pure rotations and boosts. Then we use the theorem that an arbitrary proper Lorentz transformation can be uniquely factored into a rotation times a boost. And using that theorem, then it's possible to multiply one of these matrices, these rotations, times one of these pure boosts in order to obtain the D matrix for an arbitrary proper Lorentz transformation. All right. Now, at the end of the hour last time, we just got into some of the properties of these D matrices, and I'll just mention a couple of them. One of them is that for pure rotations, the matrices are unitary, whereas for pure boosts, the matrices are Hermitian, as you can see by looking at them. If you multiply two of these together, you get a matrix for a more general proper Lorentz transformation, which doesn't really have any particular symmetry at all. It's neither unitary nor Hermitian. Of course, unitary matrices have the nice property that if we call it U, it's that U dagger equals U inverse. So it's easy to compute the inverse of a unitary matrix. But that's not going to work for the D matrices because they're not all unitary. Some of them are Hermitian. As I explained last time, the reason that we're implementing now a symmetry operation by means of non-unitary matrices is because in the case of the Dirac theory, these D matrices are only taking care of the spin part of the Lorentz transformation, and there's a spatial part as well. And when you include both parts of that Lorentz transformation, you find it's overall unitary, but just the spin part alone is implemented by matrices that are not necessarily unitary. All right. In any case, the issue of the non-unitarity of these matrices leads us to consider what happens when you conjugate things by gamma 0, because it leads to an interesting rule. And I think this is the last thing we did in the last lecture. If you take the gamma mu matrices and conjugate them by gamma 0, it's an easy calculation to show that you get gamma mu dagger. Gamma 0 is Hermitian, and the spatial parts of the gammas are anti-Hermitian, and this conjugating by gamma 0 takes care of that automatically. Likewise, if you do this for the sigma mu nus, which are the generators, I'll remind you of the D matrices, the Lorentz transformations via the D matrices, it just replaces a sigma mu nu by its dagger. Well, it's easy enough then to combine these together to obtain the following relation in the D matrices, that if you conjugate D of lambda dagger with gamma 0, it converts it into D of lambda inverse, and vice versa also. So although this is not as simple as the rule you have for unitary matrices, it means it is fairly easy to convert to find the inverse of a D matrix. You just take the dagger of it and multiply by gamma 0 on the two sides. This is a useful formula for a number of purposes, as I will now show you. And I think that takes us up to where we ended off. So before I go into any new material, let me pause and ask if there's any questions about all that. All right. If there's no questions, then I'll proceed to the new material for tonight. So the first order of business tonight is to return to the current, the Dirac current. Let me remind you that the Dirac probability density rho is given by psi dagger psi. This is a spin contraction, but there's no integral over space, so it still remains a function of space and time, but it's no longer has any spin indices. In any case, this is the positive definite probability density that Dirac found, and he was so proud because he felt he'd overcome this major difficulty with the Klein-Gordon equation, where you don't have a positive definite probability, quote unquote, probability density. Likewise, the current is given by C times psi dagger with the alpha in between, psi dagger psi sandwiched around alpha. And with these definitions, Dirac showed partial rho with respect to t plus the divergence of J is equal to 0. It satisfies the continuity equation. In fact, if you arrange these things in the form of a 4 vector with a C row as a time component and J vector as a spatial part, then the continuity equation is equivalent to partial mu J mu is equal to 0, an equation which certainly looks covariant. And in fact, it will be covariant if J mu transforms as a 4 vector under Lorentz transformations. However, that's something we haven't shown yet because it's actually somewhat difficult to do it. I mean, it's a fairly large project to do that. And but now, having gone through all the material we've been through in how the Dirac wave function transforms, we're ready to see how J transforms under a Lorentz transformation. So let me take the components of J and let me write down some formulas for them. So J0 is equal to C times rho, which, as I just explained, is C times psi dagger psi. And Ji, for the spatial component, is equal to, let me write it over here, it's C times psi dagger alpha sub I times psi, like that. Now, let me take these expressions and rearrange them slightly. I'll take the first one, write it as C dot psi dagger, and then I'll put in 2 factors of gamma 0 times psi. Gamma 0, I'll remind you, is the same as the beta matrix, and beta squared is equal to 1. So gamma 0 squared is the identity, and this doesn't change anything, inserting gamma 0 there. As far as the spatial parts are concerned, let me write this way, as C times psi dagger, that's the first part here. And then again, let me put in 2 gamma 0s, and then I follow with the alpha I times psi, like so. All right, so those are just inserting gamma 0. Now, on the other hand, gamma 0 times alpha I is the same thing as gamma I. So this second equation can be written as C psi dagger gamma 0 times gamma I times psi. And if you compare it to the J0, you got C psi dagger gamma 0 and psi sandwiched around gamma 0. Here you've got the same thing sandwiched around gamma I. So this leads to an equation that looks like this, is that J mu is psi dagger gamma 0 times gamma mu times psi. All right, collecting all 4 components into one. I'm just playing games here and rearranging some things with some fairly trivial identity, rewriting them in a slightly different form. We see here the product of psi dagger times gamma 0. Let me remind you that psi dagger is the complex conjugate rho spinner. So it's got the 4 components of psi, psi 1 through 4 in complex conjugated form, listed out as a rho spinner. And so multiplying by gamma 0 is multiplying this rho spinner on the left onto a Dirac matrix. And if you do that, you obtain what is this combination psi dagger gamma 0 is a frequent occurrence in the Dirac theory. And so it's given a special notation and a special name. It's called psi bar of x. By definition, is psi dagger of x times gamma 0. Let me box it because it's an important definition. And this is called the adjoint spinner. The adjoint spinner. And you can see that by multiplying by gamma 0, psi bar is equal to psi 1, psi 2, psi 3, psi 4, with minus signs on psi 3 and psi 4, and all 4 of the components are complex conjugated. It's the same as psi dagger, except you change the sign of the last 2. In any case, when you see psi bar, you need to remember that this is actually a complex conjugated row spinner and not a column spinner. All right, in any case, using this abbreviation for the psi dagger psi 0, which appears in the current J, there should have been a factor of C in there, we obtain the following expression that the current J mu is equal to the speed of light times psi bar gamma mu psi, like so. It's psi bar psi sandwiched around the gamma matrices. And this is an important formula because this is regarded as the covariant expression for the current in the Dirac theory. In this version of the Dirac theory we're talking about so far, this is the probability current. But in any case, this is regarded, as I say, as the covariant version of the current expression for it. Now, we still haven't shown that this transforms as a 4 vector. We need to do that, but let's talk about some transformation laws. So let me find my list of transformation laws here. So one of them is a transformation law for a spinner, which is just the same law I wrote down earlier. This was our guess that we worked out. Transformation law for a vector in space-time is given down here. We talked about those as well. if you have a vector field V mu of X, generic vector field, it transforms under Lorentz transformation lambda. This is all under Lorentz transformation lambda. What you do is you inverse transform the point at which it's evaluated, and then you multiply the value of the field by lambda. Likewise, for a tensor, you get 2 copies of the transformation matrix on the value of the field, and then the field is evaluated at an inverse transform point. This is transformation laws for vectors and tensors. Well, given the transformation, so to transform J, we're going to need to transform both psi here and psi bar. So let's work on the transformation law of psi bar. Here's the definition of psi bar down there, like that. Let's write this out as psi dagger of X times gamma 0. So under the Lorentz transformation, psi dagger goes into the dagger of the spinor transformation law. I just got psi, I have to reverse the order and dagger things. So this goes into psi dagger of lambda inverse X times gamma 0. Gamma 0 is Hermitian, so when I dagger it, it doesn't change. Let's see here. I'm sorry. I don't mean to do this. I want to transform the psi dagger of X. So this is psi dagger of lambda inverse X times d of lambda dagger. That takes care of the psi dagger part, and then the gamma 0 follows, and I have the gamma 0 like that. So this is what happens to psi dagger of X, or psi bar of X. It transforms into that. Now, where this big blue blob is, and I made a mistake, let me insert, again, 2 factors of gamma 0. Because if I do that, then I've got a psi dagger gamma 0, which is a psi bar. So I get psi bar evaluated at lambda inverse X. And then the remaining part is gamma 0 conjugating d of lambda dagger. But as I explained, that's the same thing as d of lambda inverse. And so what we obtain then is a transformation law for the adjoint spinor, as you see is summarized on this page. Psi bar goes into psi bar at the inverse rotated point times d of lambda inverse. Compare that to how the spinor itself transforms. These are the 2. All right. Now, having done that, we can now transform the current. So here's the current. Let's transform that. So J mu of X then is equal to C times psi bar of X times gamma mu times psi of X. And under the Lorentz transformation, that's going to go C psi bar of lambda inverse X times d of lambda inverse. That's for taking care of that. The gamma mu I copy. And then for the psi on the right-hand side, that goes into d of lambda times psi evaluated at lambda inverse X. All right. Let me move the page up some. And I hope I'm staying on the page now. Now, if you look at this, you see that in the middle, there is d of lambda inverse gamma mu d of lambda. But somewhere here in my summary sheets, I boxed the nice equation that we worked out. That is using the fact that gamma transforms as a 4 vector. That's this equation here that we had before. That's exactly what's appearing in the middle here. And so the stuff in the middle can be replaced by lambda mu nu times gamma nu. Now the lambda mu nu here is just the component of a matrix of C numbers. It's not spinors at all. So it can be taken out of this spinor scalar product and moved over to the side. And then what's left over is just the psi bar psi sandwiched around gamma nu, which is the current again, but evaluated at the inverse transform point. So this becomes equal to lambda mu nu, like so, times J nu evaluated at lambda inverse X. All right, so that's what happened under lambda to the original current. And this is the correct transformation law in even for classical fields, vector fields in special relativity. It is the transformation law for a vector, as you see here. And so this shows that the Dirac forcurrent actually does transform as a vector. It's a much more difficult calculation than in the case of the Klein-Gordon equation because of the spinor components here. But in any case, this then establishes the proof that Dirac's probability density and current really is satisfactory in a relativistic theory. It really does transform as a 4 vector. All right.
I have a question.
Yes, indeed.
So why did we not have to worry about transforming gamma zero when we were calculating how the adjoint transforms?
Which gamma zero are you referring to? Because uh, because that yeah, let's see, where did I do it? Right here. That right? I did it right. I did it
Mhm.
right here. Yeah, because gamma zero is just a constant matrix. I mean, I want to, if I've got this, so this is the adjoint. It's really a row spinner, right? I want to find out what happens to it when I do a Lorentz transformation on it. Well, the Lorentz transformation is going to change psi, and it's going to change the x dependence, but gamma zero is just a constant matrix. I don't know if that helps, but that's just what I've got here. Here's a transformation of the psi dagger part, and the gamma zero just got copied.
Right, but it's also the like zero component of a four vector. So it's like if we just did a Lagrange transformation to the whole thing, I'd imagine that gamma zero would change as well.
Yeah, well, gamma zero does change like that. It does transform as a component of a four vector, but it does so in this sense, right here. You see?
Right.
And remember that this is a relativistic generalization of what we call the vector, the definition of a vector operator we had last semester. That was under spatial rotations. For example, if the D were replaced by a U or a unitary rotation operator in the gamma by the poly, really, or by any vector operator, but like the poly matrices, for example, you'd have an exact analog of this formula. So the poly matrices by themselves are just constant matrices, and the same is true for the gammas here. I don't know if that helps, but to do the kind of thing you want, you need to conjugate with the D to get the linear combinations like that. All right.
Right, I see. Okay, thank you.
Okay. All right. So as I say, then the main accomplishment then on what we've done so far is to prove that J mu transforms as a four vector. If I go back to my table here of how things transform, let's talk about that. We've gotten the spinner, the adjoint spinner, and not only just a general vector, but an example of a vector, which was the Dirac current. In fact, allow me to summarize that somewhere. So Dirac, these are Dirac covariants here. We'll write them down. The vector, I'll just drop the factor of c because it doesn't matter for the vector property. The vector is psi bar gamma mu psi. That's the vector constructed out of the Dirac theory. I'll do more with this later on. We'll make this we'll make this a growing summary sheet as we find things. Now, in relativity theory, we also have tensors, for example, the field tensor in electromagnetism, and the way it transforms is with two copies of lambda that are used to transform the value of the tensor, and then the point of application, or the point that it's evaluated, is inverse transform like this. So that's a tensor transformation law. We could add to this a scalar. A scalar is one where you have S of x transforms under lambda into S of lambda inverse x. There's there's nothing done to the value of the field at all. In fact, in words, the value of the field at the old point is equal to the value of the field at the new point. That's what you mean by a scalar. Anyway, so these are some objects that transform in different ways in relativity theory. Well, in the Dirac theory, we've got a vector. Are there perhaps other quantities that we could construct out of the Dirac theory? For example, can we get a scalar? And the answer is yes. You can get a scalar out of the Dirac theory if you just construct psi bar psi. Turns out that's a scalar under Lorentz transformations, which it's an easy exercise, and I'll leave it for you to show that in case it's not obvious, but that happens to be the scalar. Let me, however, make some remarks about it. I think to remark about it, I want to remove the summary sheet and set it aside for a moment. Here's a remark I want to make, namely that as I say, psi bar psi, with using the adjoint spinner, is the scalar in the Dirac theory. But naively, you might have thought it should have been psi dagger psi, which after all is also, I mean, it sort of looks like a scalar. It's a complete contraction of a rho times the column spinner. But this is not a scalar because, well, if I multiply by c anyway, no, it's not a scalar. This is the This is actually equal to Dirac's probability density rho, which if I multiply by c becomes J0, which is the time component of a 4 vector. So the probability density does not remain, it doesn't remain constant under Lorentz transformations, but it gets mixed up with the spatial components of J as well. However, psi bar psi is a genuine scalar. By the way, in electromagnetism, we also, using a different field now, the electromagnetic field, we can also construct scalars, vectors, tensors, and so on. Scalar in the electromagnetic case would be E squared minus B squared, Lorentz scalar. This is also related to F mu nu, completely contracted on itself. We also have vectors. A vector in electromagnetic theory would be the vector potential A mu. We have tensors, such as F mu nu is the antisymmetric field tensor. There's also the stress energy tensor, sometimes called S mu nu, which is symmetric. There's others. We have, by the way, a pseudoscalar in electromagnetic theory, which is E dot B. And this is something that is invariant under proper Lorentz transformations, but changes sign under improper Lorentz transformations. So these examples of constructing various we would call them covariants, constructing various covariants in electromagnetism, we're now sort of repeating the same story in the Dirac theory, constructing first the scalar, and then as we see on the summary sheet, we also have the vector. Well, we can also construct a tensor in the Dirac theory. All we need to do is take psi bar psi, and sandwich it around the sigma mu nus, which are the generators of the Lorentz transformations. And this creates an antisymmetric tensor in the Dirac theory, which is just as good an antisymmetric tensor as F mu nu in electromagnetism. And again, I'll leave it as an exercise for you to show that this really does transform as a tensor under Lorentz transformations. In electromagnetism, we also had a pseudoscalar. The question is there such a thing in the Dirac theory also? Or how about a pseudo vector? Let me remind you that in the non-relativistic theory, we defined a vector initially by how it transformed under proper rotations. But later on, we considered improper rotations, which basically means parity or spatial inversion. And we found that there were some vectors that transformed the same as under proper rotations as improper ones, and we call those true vectors. Whereas, we call those, I didn't say it right. If the vector requires a minus sign under a proper rotation, we call it a true vector. I'm saying this wrong. Let's get it right. I'm sorry, my confusion. It's a true vector if it transforms. It's a true vector if it transforms. If it transforms under, it's a true. It's a true vector if it changes sign under an improper under an improper rotation. So, for example, the position vector goes to minus r under parity. But if it's a pseudo vector, it does not change sign under an improper transformation. For example, angular momentum r cross p goes into plus itself under parity. And so we can have a similar situation now in the relativistic theory, and we can talk about pseudoscalars and pseudovectors. So to go back to this table here, if we had a pseudoscalar, let's call it a k of x, how it should transform under an arbitrary Lorentz transformation, now including improper ones, is it should be multiplied by the determinant of lambda, and otherwise it just transforms like a scalar. Likewise, a pseudo vector, let me call it W mu of x, in contrast to a true vector v, ought to transform this way. This goes into determinant of lambda times lambda mu dot nu times W nu of lambda inverse x. Okay, like that. All right, now, can we construct pseudovectors and pseudoscalars also in the Dirac theory? And the answer is yes, but in order to address that, we need to talk about improper Lorentz transformations, which we haven't done so far. So that's the next project. Let me remove my summary sheet. And let's go on to talk about improper Lorentz transformations. The proper Lorentz transformations, I'll remind you, are combinations of rotations and boosts. The improper Lorentz transformations consist of the parity or spatial inversion operation and time reversal. Now, because we're running toward the end of the semester, I'm going to ignore time reversal in a discussion of improper Lorentz transformations, and for simplicity, just concentrate on parity. It's a simpler one anyway. So let's talk about parity. Let's let that be the only improper Lorentz transformation that we'll talk about. If I have a Dirac wave function psi of x, which I can also write as psi of ct comma x vector, breaking its up in its x dependence in the space and time portions, you might suppose that under spatial inversion, what we're calling p, by the way, p here is the matrix 1, -1, -1, -1 like this, does nothing to the time coordinate and flips the 3 spatial coordinates. In any case, under spatial inversion, you might expect, based on what we did in the non-relativistic theory, that this should go over into psi of ct comma minus x, that it should just simply change the x, flip x into minus x and do nothing else. Because that's what happened in the non-relativistic theory, including for particles with spin. The parity did nothing to spin, remember? Okay, so the question is, will this work in the relativistic theory? The answer is, it turns out it doesn't work. It actually doesn't work. And let me explain why and what we need to do to fix it. Here is the issue. We actually need to insert in here a matrix that modifies the spin part of the wave function as well. Let me call it d of p here, which is a generalization of our earlier notation. You know, under the proper Lorentz transformations, we agreed that psi of x should go into d of lambda times psi of lambda inverse x. So for the case of p, which is an improper rotation, let's guess that psi of x goes into d of p, which is to be determined, a 4x4 Dirac matrix, times psi of p inverse x. I write this as p inverse x just to make it look like what we did earlier with the proper rotations. However, the p matrix is actually equal to its own inverse. And so psi of p inverse x is really the same thing as psi of ct comma minus x. It's just what we guessed up here for the transformation property for the space-time part. But let's write it this way so it looks like what we did before. What's new here is the d of p. So d of p is not known at this point. We don't know what it is. So here's what we're going to do. We're going to suppose that under parity or under spatial inversion, psi transforms in this manner. But we'll try to determine what d of p must be in order to satisfy reasonable criteria. And we'll keep an open mind as to whether or not it might turn out that d of p could be the identity. And if that were true, then we wouldn't need the d of p up here in this upper formula. It would just be the obvious transformation law. So the question is, will d of p equals identity work? All right, now here's what we're going to do. We're going to demand that, as we did with the proper Lorentz transformations, we will demand that this transformation map every solution of the free particle Dirac equation into another solution of the free particle Dirac equation. This is effectively a way of saying that the free particle Hamiltonian ought to commute with parity. So if we make that demand, then we can go through the analysis of the condition on d of p. And the analysis is exactly the same as we did earlier with d of lambda, and it leads to the same conclusion, namely that d of p inverse times gamma mu times d of p should be equal to p mu nu times gamma nu. It's just replacing p by lambda or lambda by p. It's the same formula we had before, and it's derived in exactly the same way. So this is a condition which is necessary. As I say, it's in effect a way of saying that the Dirac equation has the same form when subjected to parity as a free particle Dirac equation when subjected to parity as it had before the original form. All right, now let's break this up into its space-time parts. If I set mu equals to 0, what I get is d of p inverse times gamma 0 times d of p. is equal to gamma 0, because you're just getting the +1 part of the P matrix, that thing right there for the time part. On the other hand, if I set mu equals I for a spatial part, we get d of P inverse times gamma 0 times d of P is equal to minus gamma I. These spatial parts change sign because there's minus signs for them, for that part of the spatial inversion matrix. Now gamma 0 is the same thing as gamma 0 dagger, and because gamma 0 is Hermitian, but the gamma i's are anti-Hermitian, so minus gamma I is equal to gamma I dagger, like this. And so we see that d of P, whatever it is something that when we conjugate it, this should have been gamma I here, but when we conjugate it around the gamma matrices, it takes them into the Hermitian conjugates. Now, by the way, one of the things you can see right away is that the identity will not work because it wouldn't satisfy this gamma I equation here. It would map gamma I into itself, not into minus itself. So this is not going to work. We must have some D matrix in here. The naive guess was wrong. But the question is, what is the D of P that'll do it? Well, let me remind you that conjugating the gamma mu by gamma 0 converts it into gamma mu dagger. So the D of P needs to have the same property. And so this leads to the conclusion that D of P, at least a solution of these equations, is that D of P is some phase factor e to the I alpha times gamma 0. All right, so this is something that needs to be put in there. The phase factor e to the I alpha is not determined by these conditions. However, we can look at further conditions which the D of P matrix ought to satisfy. It ought to satisfy the multiplication rules and representation of the multiplication rules for the Lorentz transformations. Here's some of them that are worth looking at. If you square the spatial inversion operator, you get the identity. That's kind of trivial. Another one is if you multiply it times a proper rotation, let me call it R of n hat theta, you find that it commutes with it. Spatial inversion commutes with proper rotations, as you can convince yourself by, rotating your fingers and thumbs and stuff. Or you can also look at the generators of the rotations and see that they actually commute with the spatial inversion. On the other hand, parity or spatial inversion, when it acts on a boost, a b hat comma lambda with some rapidity, what it does is if I bring it through, it changes the rapidity to minus itself, like so. Again, this is easily verified by looking at the formulas for the boosts. These two formulas make sense because the generators of rotations, of course, is the angular momentum, which is a pseudo vector and which doesn't change sign under parity. Whereas the generators of the boost are the velocity vector, and the velocity vector is a true vector and does change sign under parity. That's why lambda goes to minus lambda. In any case, these are requirements that need to be satisfied, or excuse me, these are requirements which are satisfied by classical Lorentz transformations. Well, then the representation property, looking at P squared equals I, tells us that D of P squared should be equal to +1. And that means that this phase factor can only be a plus or minus 1. And so we get D of P is equal to plus or minus gamma 0, like so. Let me box that because that's kind of the end conclusion of the derivation of the spin matrix needed to implement parity. You can show that if with this form of D of P, you can show that these two properties are preserved in the representation. For example, replace P by D of P and rotations and boosts by the corresponding D matrices, you'll find these equations work out. So this is a completely satisfactory, based on the criteria that we've laid down, this is a completely satisfactory definition then of parity, of the spin part of the parity transformation for the Dirac wave function. All right, now,
Professor,
yes.
can I just quickly ask about, we know that in quantum mechanics, is we're interested in projective transformations, we always allow for phases.
Yes.
How do we know that we can always eliminate that phase for when we have parity?
Yeah.
See, I don't.
Yes. Yes. Recall what we did with rotations. we look for it's a simpler problem. We looked at representations of the rotation group. We called that, those were the, we called them U operators, right? And so they were operators that acted on wave functions, maybe with or without spin. And we did require that those U operators reproduce the multiplication law. So that's an ordinary, for the rest of you, by the way, wondering what a projective representation is if the operators reproduce the multiplication law of the group operations directly, then that's an ordinary representation. But if it only represents them to within a phase, if there's extra phase factors that comes in, then it's called a projective representation. And basically, we used an ordinary representation, not a projective one, because we could get away with it. So to answer your question, I think the answer is that we can get away with it. You can do it here. I mean, you can get a projective representation and it works. So we don't complicate it by adding phase factors. If you study the problem of an electron moving in the field of a magnetic monopole, from the standpoint of quantum mechanics, the quantum mechanical problem of that, you will find that you cannot implement rotations as an ordinary non-projective representation. You need phase factors to give a projective representation. And that's the tip of the iceberg of quite a big story about projective representations, and typically they're lifted versions and stuff. Anyway, let me stop the tangent because it's too big a subject, but I hope that answers your question. Basically, we do it because we can. Here, it's the simplest thing to do and it works. I think that's the easiest answer. All right. In any case, we then obtain this expression then for the matrix representing parity. Now, what about the plus or minus sign? It turns out there's no physics in that, and it's a matter of convention. But here's what it means. If I choose the plus sign, I mean, notice the gamma zero. Gamma zero's got this 1, 0, 0, -1. So it's a +1 in the upper two components and a -1 in the lower two. That's what gamma zero is. If you choose the plus sign, what it means is that the intrinsic parity of the fermion in question, spin 1/2 fermion, is plus, whereas the intrinsic parity of the antiparticle is minus. And so that's the lower half here. I'm very much getting ahead of the story here by even talking about antiparticles because we haven't seen them yet in the Dirac theory. You need to go through the second quantization and so on to get to that, or at least whole theory to understand that. And we won't have to, unfortunately, we lack about 1 or 2 lectures to be able to do that this semester. So we won't be able to do that. But when you do go through that, that's what you find. Whereas if you chose the opposite sign, you would be assigning the particle, the quote unquote particle, as having negative intrinsic parity and the antiparticle having positive. The main point here is that the fermion particle antiparticle pair taken as a unit has negative intrinsic parity. That the two particles have opposite intrinsic parity, and that's what this plus or minus sign means. Normally we'd end up taking the plus sign here, like for electrons, and so that's what I'll do for the rest of what's left of this course, which isn't much. We'll just take a plus sign there for the parity operator. All right. So this gives us then the action of now improper rotations on parity and parity. All right. All right. Now then let's go back then. So now we know we now know at least about parity as an example of an improper Lorentz transformation. Is there, for example, a pseudo scalar in the Dirac theory? The answer is yes, but I have to hold on to your seat. In order to talk about that, I have to introduce yet another Dirac matrix. This one is called gamma 5. And gamma 5 is written as either with a superscript or a subscript. It doesn't matter. It's the same matrix. And the definition of it is that it's I times gamma 0 times gamma 1 times gamma 2 times gamma 3. Now, this needs to be added to our menagerie table, wherever it is, if I can find it here, of Dirac matrices. Here it is. Here's the non-covariant and the covariant list. We'll add the gamma 5 to the covariant list. It's normally considered that. So this is the last of the Dirac matrices that I need to talk about. And here then is a total collection of them. You can see it's maybe not so bad, but that's what it is. Anyway, so that's the definition of gamma 5. And why do they call it 5? In the first place, the position of the index doesn't matter whether it's upper or lower. It's the same matrix. The reason they call it gamma 5 is because it's a way of defining yet another gamma matrix without wasting another letter of the Greek alphabet, which are kind of getting exhausted by all the matrices we've defined so far. That's really the reason for it. They don't call it gamma 4 because the 4 is used for the ancient ICT, x equals x4 coordinate when people used a complex metric and special relativity. In older books, you'll find people still use or used to use that, but nowadays nobody does anymore. So anyway, but to avoid confusion with the old x4, we now have and there's a corresponding gamma 4. Anyway, we call this gamma 5. Well, in any case, it's just a new Dirac matrix, and here's its properties, which I'll list for you. So it has the following properties, which are all easy to verify. One of them is that gamma 5 is Hermitian. The second one is that gamma 5 squared is the identity. The third one is that gamma 5 anti-commutes with gamma mu. And the fourth property is that gamma 5 not anti-commutes, but commutes with sigma mu nu, which is, of course, the Dirac tensor set of Dirac matrices. I won't prove all of these properties here. All of them are straightforward to prove, but let me just take 3 and just give you an example of this. Let's take gamma 5 times gamma 2, for example. This is I, gamma 0, gamma 1, gamma 2, gamma 3, and then the gamma 2 stuck on the end. Now, gamma 3 and gamma 2 anti-commute with each other. So this is minus I, gamma 0, gamma 1, gamma 2, gamma 2, gamma 3. I just swap these two and change the sign. The gamma 1 and gamma 2 anti-commute, so it becomes plus I, gamma 0, gamma 2, gamma 1, gamma 2, gamma 3. And then the gamma 0 and gamma 2 anti-commute, and so this becomes equal to minus I, gamma 2, gamma 0, gamma 1, gamma 2, gamma 3. And you can see that this is minus gamma 2 times gamma 5. So bringing that over to the other side, we have the anti-commutator of gamma 5 with gamma 2 equals 0. And by a similar analysis, you can replace this 2 by any mu whatsoever, and you can then verify this formula number 3. And I won't do any of the others because they're all equally straightforward to do, just starting from the definition. But these are the properties of gamma 5. Now then, the fact that the d of p is equal to gamma 0 means that gamma 5 anti-commutes with the D matrix for an improper rotation, the only one of which we have now is parity. But the fact that gamma 5 commutes, not anti-commutes, but commutes with sigma mu nu, which are the generators of the proper Lorentz transformations, means that the gamma 5 commutes with D of lambda if lambda is proper. So this is the distinction then between proper and improper Lorentz transformations. Now then, we can start to construct some covariance. If I take psi bar and sandwich it around psi bar psi and sandwich it around gamma 5, this is of x and of x like this. Then under the Lorentz transformation, this turns into psi bar of lambda inverse x times d of lambda inverse times gamma 5 times d of lambda times psi of lambda inverse x. And this formula actually applies both for proper and improper Lorentz transformations. Now, if d of lambda is proper, however, this then it commutes with d of lambda. So I can move the gamma 5 past it. The d of lambda inverse cancel, and so this turns into just gamma 5 if lambda is proper. But if lambda is improper, namely proportional to gamma 0, that's the only one we've got is d of p is gamma 0. then since gamma 5 anti-commutes with the gamma mu's, in particular with gamma 0, when I move the gamma 5 past gamma 0, I get a minus sign, and gamma 0 squared is 1. So this becomes minus gamma 5 if lambda is improper. And so what we obtain then is that psi bar gamma 5 psi transforms under lambda like this into determinant lambda. If I call this k of x is equal to this, it turns into determinant lambda k of lambda inverse x, which is the pseudo-scalar. And so to go back to our Dirac covariance, we get the pseudo-scalar by taking psi bar and sandwich around gamma 5. In the brief time we have left in this course, I won't be doing really anything with pseudo-scalars or pseudo-vectors, but for completeness, on the story of the covariance, I need to go through it. But let me just mention that neutrinos famously violate parity. And so the gamma 5 plays an important role in the theory of the neutrino. By the way, the pseudo vector is going to be psi bar gamma 5 gamma mu psi, as compared to the true vector, like the current. You've got just a gamma mu in there, but you put a gamma 5 and it turns it into a pseudo vector. And again, pseudo vectors play an important role in the theory of the weak interactions. All right. Okay, so these then are the Dirac covariants, and this is then the end of the story on the collection of Dirac matrices. I'd now like to say some things about the Dirac algebra. This is Dirac algebra in a different sense that I used earlier, the algebra of the Dirac matrices. One of the ways of defining an algebra, this is close to how they do it in a math book. If we speak in terms of matrices anyway, you can do it this way. If you have a set of matrices, which we call the generators of the algebra, then the algebra is the set of all matrices that can be formed by multiplying the generators together and then forming all possible linear combinations of the products that you can form. In a sense, it's a set of all possible polynomials that can be created out of the generators. Except since the matrices in general don't commute with each other, a monomial like AB is not necessarily the same as BA. In any case, that's the idea. So to show you how this works out, for example, in the case of the Pauli matrices, if I have the sigma I, the 3 Pauli matrices like this, if I take any one of them and square it, sigma I squared, I get equal to 1. So the algebra includes not only the 3 Pauli matrices, but also the identity matrix. That is to say, it includes monomials that are of 0th degree in the sigmas and monomials that are 1st degree in the sigmas. What about quadratic monomials in the sigma, sigma I, sigma j? Well, by the identity involving the Pauli matrices, this is delta ij plus I epsilon ij k sigma k, which, as you see, is a 1st degree polynomial in the sigmas. And so as a result of this identity, all higher order monomials in the sigmas can be reduced to 1st degree. And therefore, the Dirac algebra is really spanned by these matrices 1 and sigma I, and that's the end of it. Well, 1 and sigma I, as you know, or if I make a sigma vector here like this, the set of 4 matrices, as you know, they span the space of all 4 by 4 matrices. And so in this sense, the Dirac algebra is actually equal to this, the Pauli algebra is equal to the set of all possible 4 by 4 matrices. Now let's do something similar with the gammas, gamma mu's. This, of course, gives us 4 matrices. Oh, by the way, if I made a table here, there's 1 of these plus 3 of those, which equals 4. That's, of course, what you need in order to span the space of 2 by 2 matrices. So let's take the case of the gamma mu's. Let's look at the algebra generated by the gamma mu's in the same sense that I just described. If I take the gamma mu, any one of them, and I square it, I'm going to get plus or minus 1. For example, gamma 0 squared is equal to plus 1. So the Dirac algebra includes the identity as well as the gamma mu's. Let me make a table here. So the matrix or matrices, and then the number of them. We have the matrix 1, there's only 1 of them. We have the gamma mu's, there's 4 of them. Okay, now I'll leave some space here and go to a new page and continue the story of the algebra. So to continue the story of the algebra, we'd want to know now about quadratic expressions in the gammas. Well, let's look at a quadratic monomial in the gammas, gamma mu, gamma nu. There's nominally 16 of those. However, the gammas satisfy the anti-commutation relations, which is the fundamental anti-commutation relations of the gamma matrices, so that of the 16, the symmetric part, in effect of this tensor in mu and nu, is reducible. This is multiplied by the identity, you see. It's reducible to something proportional to just the one. So this is not new. It's only the antisymmetric part of this which is new. Well, the antisymmetric part, gamma mu, gamma nu, if I multiply by I over 2, which is just a normalization factor, that gives me the sigma mu nus, of which there are 6, because it's antisymmetric in indices mu and nu. So we end up adding another set of now basically quadratic expressions in the gammas, and there's 6 of them. All right. Now then, to get the next set, here's what we do. We take gamma mu and we multiply by gamma 5, our gamma 5 that was used for talking about parity a minute ago. To show you what this does, let's take the case mu equals 2, for example. So we have I, gamma 0, gamma 1, gamma 2, gamma 3, gamma 2. Okay? If I anti-commute the gamma 3 and gamma 2, I get I minus I, gamma 0, gamma 1, gamma 2, gamma 2, gamma 3. But gamma 2 squared is minus 1. So this becomes plus I, gamma 0, gamma 1, gamma 3. And this is an example which shows you that gamma 5 times gamma mu is actually a trinomial, it's actually a monomial of degree 3 in the gamma matrices. And whatever index mu here is equal to the one index that's left out in the product of them. Here it's 0, 1, 0, 1, 3, the 2 is left out. That's equal to gamma 5, gamma 2. So as a result, there are 4 of these because mu runs over the ones that are left out. So let's write this up here. We have gamma 5, gamma mu, and there's 4 of those. And so the degree 3 monomials or polynomials have just 4 independent ones, and here they are. Finally, what about monomials that are of 4th degree? Well, there's really only one of those, and that's gamma 5 itself. Like this. That's gamma 5. You could rearrange the 0, 1, 2, and 3 in a different order, but by using the anti-commutators, you could bring it back to gamma 5 to within an overall sign. So to within a sign, the ordering doesn't matter. Also, if any of the indices that I'm listing up here were identical to one another, you could anti-commute them to put the 2 identical ones neighboring next to each other, and then they'd square to give you plus or minus 1. And this would be reduced from a 4th degree monomial down to a 2nd degree monomial, and we have those already. So the only ones that are new are where all 4 indices are distinct, and that gives you essentially just one matrix. So that's the gamma 5 here, appears here in our table. Then this is the last one, which has 1, like so. And if you add these up, you see you'll get 16 matrices, just like we had 4 in the case of the Pauli matrices. So this is in some sense the algebra that's just generated by the gamma mu, using the word algebra in this sense. And that consists of 16 matrices. It turns out, as in the case of the Pauli matrices, these 16 are linearly independent. And so any 4x4 Dirac spinor matrix can be represented as a linear combination of these. These are called the bilinear covariance, or bilinear covariance are what you get when you sandwich psi bar psi around them. But in any case, as far as the matrices goes, these are the sets of matrices that have the various transformation properties. This is important in constructing theories in particle physics. For example, if you have an interaction that preserves some symmetry, like parity, for example, this is going to govern which of these Dirac matrices are allowed in an interaction Lagrangian and which ones are not. Or you may be interested in exploring the possibility of violation of some symmetry, and so you put in an extra term that involves one of these things, and then you calculate a cross section to see how big it is. So this type of operation is used. This type of logic of these matrices is used quite a bit in particle theory. Okay, that takes me up to everything I wanted to say about the Dirac matrices. It's actually quite a lot. Are there any questions before I move on to the next topic? All right, if not, then I will move on to the next topic. And I'll do so by putting some papers away. A clean sheet. All right, at this point, I want to tell you about the Foldy Wouthuysen transformation. Wouthuysen, and Wouthuysen is Dutch, and so you can't pronounce his name correctly unless you're born Dutch, which I'm not, but it's something like that. I'm presenting this material with some hesitation because if I skipped it, I'd have more time to work towards the whole theory of the Dirac field and the second quantization, which is an interesting subject, and I expect some people are interested in it. However, I can look at the clock and see that even if I skip this stuff in the Foldy Wouthuysen transformation, there still won't be time to do that, and so there's no hope anyway. And on the other hand, the reason for doing the Foldy Wouthuysen transformation is that it actually derives the fine structure that we saw last semester from the Dirac equation. That's the point of doing it. And this makes a nice, I think, way to conclude the second semester of cleaning up some of the hand wavy and pseudo derivations that we gave last semester for these relativistic corrections. These rather non-trivial relativistic corrections. They all come out of the Dirac equation, and so that's what I'm going to show you tonight, or at least get started on it. So so that's the basic idea of the Foldy Wouthuysen transformation. We took the Dirac equation earlier and we carried out a non-relativistic approximation to order V over C squared using ad hoc techniques. You know, we eliminated the chi in terms of the phi, if you'll recall, and it ended up with the Pauli equation. And this allowed us to determine that the Dirac particle is equivalent to a Pauli particle of spin 1/2 with a G factor of 2. In other words, it's giving us a theory of the electron with the right G factor. But that was only through order V over C squared. And what I'm going to do tonight, or make a start anyway, is carrying out the non-relativistic approximation out to order, not V over C squared, but V over C to the 4th power. So it turns into a rather serious perturbation calculation, which I'll now show you how it works. So before we begin, I want to make a bit of introduction. First of all, I'm going to use the natural units, what are called natural units, because it saves writing. Natural units are useful in relativistic theories. That's where h bar equals c equals 1. If you're in natural units, the fine structure constant, which in ordinary units is e squared over h bar c, just becomes equal to e squared. So you see the electric charge in natural units is 1 over the root 137. It's a small parameter in problems involving QED. As I say, I basically want to do a power series expansion in powers of V over C. Now, of course, whether V over C is small or not depends on the system. And so what we need is to have some kind of a reference system. And also we need to order not only the velocity, but we need to order other quantities too, such as electric fields and potentials and things. And you can't carry out an ordering like that of all these quantities unless you choose some physical system as a reference system with which to refer the ordering parameters to. So what I'm going to choose as the reference system is the ground state of hydrogen. It's obvious choice. That'll mean that as an order of magnitude, everything we're doing works for any other system whose V over C and other parameters are comparable to that of the ground state of hydrogen. So that would mean most atoms, at least the valence electrons of them, and most problems involving molecules and in condensed matter physics as well would work for the ordering scheme that I'm going to present. On the other hand, if you're studying, for example, particle motion in the magnetic field of a neutron star, where it's 10 to the 15th Gauss or something, if it's a magnetar or something like that, then the ordering scheme I'm going to present is not the right one, and you need to rethink it. Okay, so with that understanding, let's proceed and worry about how things are ordered. So I'm going to call the ordering parameter eta. The eta is basically order V over C, and of course in the ground state of hydrogen, that's also the same thing as the order. It's an order of the fine structure constant. So eta numerically, if you like, basically is the same as the fine structure constant, or it has a value of something like 1 over 137. But I'm going to call it eta instead of alpha because I want to reserve the symbol alpha for the Dirac matrices, so it avoids confusion if I do that. And in fact, I'm really only going to use the symbol eta in the following presentation as just a reminder of the order of magnitude of the various terms. Otherwise, we'll never use it, never try to assign a value to it. All right. Now, in natural units, the c goes away. So the velocity itself is of order eta based on our assumptions. Let me make a table here of a quantity that we're interested in the order of magnitude that we're going to give to it. So the velocity is going to be order eta to the first power, according to what we just said. I'm going to take the mass of the particle and consider it to be order eta to the 0 power, which is the same thing as 1, order unity. This is basically just a way of setting the energy scale for the calculation. It's going to be basically mc squared, but c is 1 here. So that's the mass. And so you have these orderings. This means that m times v, I'll put a vector on it, which is otherwise the kinetic momentum pi. This is also order eta to the first power because the mass is order 1. It means the non-relativistic kinetic energy 1/2 mv squared is of order eta squared, like that. Again, using hydrogen as a reference system, you've got an electron which moves on an orbit, and as it does so, there's an interchange between kinetic and potential energy, trade back and forth. And as a result, the potential energy, which is q phi, has to be the same order as the kinetic energy, so that's also eta squared. So you can start to fill out a table of the order of magnitude of various terms. Let's talk about length and distance scales too. Let's start with the Compton wavelength, which in ordinary units is equal to h bar c divided by the mass m, except in natural units that just becomes 1 over m. And so we see that the Compton wavelength is of order eta to the 0 equals 1. It's of order unity in these units that we're in this ordering scheme that we're using. On the other hand, the Bohr radius A0 is equal to the Compton wavelength divided by the fine structure constant. And so A0 is actually of order eta to the inverse 1, inverse power. In other words, the Bohr radius is large in this ordering scheme. Let's talk about time. Let's let T0 be the orbital period of the electron in the hydrogen atom. This can be written this way as h bar divided by mc squared times alpha squared, the fine structure constant squared, which in our natural units just turns into alpha squared. Excuse me. Let's see here. Yes, that's right. Turns into, just a minute here. No, it's alpha to the -2. It's 1 over alpha squared. I knew I was doing it wrong. It's 1 over alpha squared. This time is really very short. It's 10 minus 23 seconds. We divide by alpha squared, which is like multiplying by 10 to the 4th, and it brings it down to the atomic time scale. So this goes like, as you see, since alpha is the same as eta, this becomes eta to the -2. The h bar and c go away, and it's 1 over m. All right, so the T0 is eta to the -2. Now this means the gradient operator, if the fields you're taking are, vary on the atomic scale A0, the gradient operator goes like eta, because it's the inverse of this, goes like 1 over A0. And likewise, the time derivative operator, assuming the time dependence is determined on the atomic time scale, goes like eta squared. This is a small operator. All right, now then, let's look at the longitudinal electric field. Let's multiply by q. This becomes minus q times the gradient of phi. But q phi we decided was eta squared, and the gradient operator is order eta. So the longitudinal electric field times q is order eta cubed. What about the vector potential, A? Let's multiply this by q. If you do a little bit of electromagnetism in the Coulomb gauge, you'll find that the A vector potential goes like V over C times the scalar potential. If you just look at the Biot-Savart law or the equivalent of that for the vector potential, you'll see this is a factor of V over C in there. So QA is basically Q phi with another factor of eta, that's order eta cubed. That means that Q times B, which involves the curl of A, And since the gradient involves order eta, this is order eta to the fourth magnetic field. The transverse electric field, Q times E transverse, which is equal to minus Q times dA dt. Well, the A is QA is eta cubed and ddt is eta squared, so this becomes eta to the fifth power. This becomes quite small. All right, so anyway, in this manner, we obtain a table that gives us how we're going to order various quantities in the perturbation expansion we're going to do. All right. So I'll need to refer back to this. I'll keep this page here, but let me maybe I can just start on a new page. Let me refocus it and make sure it's. And let me try to brighten it up a little bit. Hopefully, I can do that. Oh, that was too much. There, is that better? I think that's better. All right, let me keep this. Let me keep this page and put these others aside. All right, so here's what we're going to do. We're going to write using h bar equals c equals 1. We're going to write down the Hamiltonian for a Dirac particle interacting with an external electromagnetic field. And we'll write the Hamiltonian in the following way. First of all, the mc squared beta term just becomes m beta, and I'm going to put that term first. Then there's a term which is c alpha dotted into pi, where pi is the kinetic momentum. Pi is equal to p minus q times a in natural units. So this is the kinetic momentum. It was alpha times pi. I'll put that term next. The c I skip because it's natural units. It becomes alpha dotted into pi. That's the next term. And then the last term is q times capital phi for the scalar potential. It's just a rearrangement of the usual terms and putting things in natural units. Now the m beta is order eta to the 0 power, so it's the dominant term by our ordering scheme. By the way, the Dirac matrices alpha and beta, of course, are order unity because they're just numbers that have ones, more or less ones and minus ones in them. That's all. On the other hand, the pi, which is the kinetic momentum from our table up here, is order eta to the first power. So the second term is order eta to the first power. And the q phi, as you see, is order eta squared. So the three terms in the Dirac equation have different orders in powers of v over c. And we're going to want to now carry out a perturbation expansion now. The strategy or the goal of the perturbation expansion is going to be to decouple the Dirac equation, which involves, of course, a 4-component spinor, but to decouple it so it becomes two uncoupled equations involving two 2-component spinors. To do that, it's useful to classify the Dirac matrices as either being even or odd, and I'll show you what I mean by that. The even Dirac matrices include the following one. There's first of all the identity, which in 4x4 notation looks like this. Then there's the beta matrix, which looks like this. It's 1, -1 on the diagonals and 0. So the even matrices are ones which are strictly diagonal in the block diagonal and zeros in the off diagonal. Another even matrix is sigma, the generator of rotations, which is Pauli sigmas on the diagonal and zeros in the off diagonal. The odd matrices include the alpha matrix, which is sigmas on the off diagonal. And it also includes gamma phi, but I won't need gamma phi for what I'm going to do, so I won't write that out. But anyway, here's the breakdown into even and odd. Now what you can see is that the eta to the 0 term is even because it's beta, and the q phi term is even because it's just a multiple of the identity. But the eta to the first power term is odd. So what we'd like to do is to take the matrix for the Hamiltonian and to eliminate the off diagonal elements, which is to say the odd contributions. So in particular, we want to get rid of this eta to the first power term here, eta to the first, which has got the off diagonal elements, so that we end up with just the even parts. That'll be the goal of the perturbation expansion. Okay, here's how the perturbation expansion is going to work. It's going to be a novel form, at least for this course, of perturbation theory. It's not bound state perturbation theory like we did before. It works like this. Let's take the original Dirac equation and write it this way: as I partial psi with respect to t is equal to h psi. And let's write psi prime, a new wave function psi, is equal to e to the s times psi. We'll call S as the generator of the transformation, and we'll demand that it be anti-unitary. Because if we do that, then e to the s is a unitary transformation. So this is just taking the old wave function and mapping it into a new one by means of some unitary transformation.
Did you mean anti-Hermitian?
I do mean anti-Hermitian, thank you. Anti-Hermitian for S, but unitary for e to the s, thank you. Who knows what I'll say at this hour of the night. Okay, so let's make this substitution into the Schrodinger equation. So we get I d psi prime dt, just using the chain rule, as I ddt applied to the e to the s part times psi, plus e to the s times I d psi dt. And as far as the first term is concerned, we can write this way, is equal to I times d partial e to the s with respect to t times e to the minus s times e to the s times psi, but that's the same as psi prime. Basically, I inserted an e to the minus s times e to the s in here. Likewise, over here, the second term becomes e to the s, just copying this, and I d psi dt is h times psi. They'll write that as e to the minus s times e to the s times psi, and this part becomes a psi prime. And the result of this is that we get I times partial psi prime with respect to t is equal to h prime psi prime. The Schrodinger equation is restored to its original form if h prime is equal to e to the s times h times e to the minus s plus I times d of e to the s dt times e to the minus s. All right. And this is the transformation law for the Hamiltonian under this unitary transformation, including a time-dependent term, as you see, and it maintains the form of the Schrodinger equation. All right. Now, way back at the beginning of the fall semester, you'll remember the very first homework problem in which expressions like these two expressions were expanded in power series of iterated commutators. And I want to remind you of the results of that homework problem. In the first place, looking at the first term, e to the s times h times e to the minus s can be expanded. If you expand out these exponentials of this generator s. By the way, this generator s that we're going to be dealing with here is going to be in some sense small. In fact, we'll find out that initially it's of order eta. It's of order v over c. And the reason for that is that we need to, when we transform the Hamiltonian, the goal is going to be to get rid of the first correction term. That's the one that's odd. So it's down by a factor of eta from the leading term, which we don't change. That's the idea. So in any case, S is in a sense small. And so it's reasonable to expand these exponentials in power series. And if you do, this can be this result of conjugating h by e to the s can be represented as a power series of iterated commutators. It looks like this. You get h plus the commutator of s with h plus 1 over 2 factorial times the second commutator of s with h, and so on like this, plus dot, dot, dot. This is how it worked out in that homework problem. It's useful to have some notation for commutators. Let me use the following notation. I'll write LSX like this. X is any operator. LSX is, by definition, is the commutator of S with X. LS squared X is the iterated commutator, S with X, and so on down. LS to the 0 power acting on X, we'll just say that's X alone. So LS to the 0 power just is identity. Let's use this notation. Then if we do, the e to the s times h times e to the minus s becomes equal to h plus ls times acting on h plus 1/2 ls squared acting on h plus higher order terms. Likewise, if we refer to that homework problem from last semester, I times e to the s over t, derivative, I times partial e to the s over t times e to the minus s, this is equal to I times s dot plus 1/2 the commutator of, well, let me write this way, 1/2 of L sub s acting on s dot plus higher order terms like that. This is a way of writing it out. All right. And so with this original H, which is up here, this is the H ordered in 3 terms, the even one, the odd one, the even one. And with the H prime given by this formula, if I want to write out the H prime for some arbitrary S, I need to conjugate all 3 of these terms by e to the S, which generates these exponential series. And I need to also include the term for the time dependence. So this is going to give me now an H prime that looks like this. H prime is going to be equal to m beta plus LS acting on m beta plus 1/2 LS squared acting on m beta plus 1/6 LS cubed acting on m beta plus 1/24 LS to the 4th acting on m beta. We're going to go to 4th order, you see, because this is 4th order perturbation theory. But you'd never do one of those. But you thought you'd never do one of those. But here it is, 4th order perturbation theory. Anyway, that's just the m beta term. Then comes the next term, which is alpha dotted into pi. Now I'm going to make some abbreviations here. I'm going to write alpha dotted into pi, which is the 1st order term in this Hamiltonian. I'm just going to call it O, script O here, which means odd. And I'm going to call Q times capital phi, which is the even term at 2nd order. I'm just going to call it script E, which stands for even, because it's easier to write O and E than it is to write alpha dot pi and Q phi. So anyway, if you'll allow me to do that, make that abbreviation. Then continue with H prime, we have, first of all, we have O here. Then we have LS acting on O. Then we have 1/2 LS squared acting on O. And then we have 1/6 LS cubed acting on O. And then likewise for the even term, we've got E here, plus LS acting on E, plus 1/2 LS squared acting on E. And then there's higher order terms. And then we've got plus the S dot terms that came from the time derivative. Okay. So this is the transformed Hamiltonian now under more or less arbitrary S. However, we're going to choose S, the generator of the unitary transformation, to kill off the O here. So we want to choose S such that LSM beta, which is LSM beta, which is otherwise equal to the commutator of S with M beta, which is otherwise the same thing as the mass M times the commutator of S with beta, various ways of writing it, shall be equal to minus O, which is minus alpha dotted into pi. It's the first correction term in the Dirac equation. Now, if you write the unknown S as a Dirac matrix with decomposed into its 4 blocks, and you just compute this beta, of course, we know what that is. It's this 1 minus 1 on the diagonal. So it's easy to work out the commutator and set it equal to minus O. It's easy to work out what S is. And I'll skip the algebra of that. But it turns out that S becomes equal to 1/2m times beta times O, like that. So this is the generator which results. Now the O term is the alpha dotted into pi, which is of order eta. So our S is actually of order eta. That's natural because we're using it to eliminate the O term here. That's what made S of order eta. But that means is LS squared, cubed, and so on, a progressively higher power. Each one is 1 higher power of eta. So we've got an eta to the 0 here and eta to the 1, which is getting canceled completely. Eta squared, eta cubed, and eta to the 4th. If I list all the columns here, the various terms of this expansion. All right. So it is straightforward to check that this S actually satisfies the equation we want. LSM beta is equal to minus O. And with that, I can see that I'm out of time. In fact, I ran over a little bit. I apologize. It's a bad place to end when you're right in the middle of a hairy calculation, but I can't do anything about it. So we'll resume this next meeting on Thursday. I'm sure that we'll be able to finish the Foldy Wouthuysen transformation. You'll see how that works out. And then I'll do a couple of cleanup topics on interesting aspects of what is called the first quantized Dirac theory. It basically means the Dirac equation we've been dealing with to try to make the content of the semester close in a reasonable way. So that's all for tonight, unless there's any questions about this. This procedure of carrying out perturbation expansions as a sequence of iterated or sequence of unitary transformations, which simplify the Hamiltonian to progressively higher and higher orders. This is a certain philosophy of perturbation theory, which is not what we used in bound state perturbation theory last semester, but it's oftentimes very useful. And there's a number of problems that can be dealt with quite nicely this way. One of them is the problem that explains why atoms are trapped inside optical lattices, which is a question one of the students was asking me about the other day. Another one is the Born-Oppenheimer approximation, which can be carried out by this kind of a sequence of unitary transformations. There's quite a few problems that are best handled in this manner, which would take another 221C course to go into, so I won't be talking about it. Okay, that's all. Unless there's any more questions, that's all for tonight. I'm going to stop the share screen. All right, here we go. That's the end.